Okay, yeah, so I made my title shorter, just talking about a large neural network for chemical hazards. The earlier speaker talked about trajectories in machine learning, so really I'm just going to be giving you a trajectory, what we've done in the past, what we're doing now, what we're going to be doing in the next year or so. Yeah, there we go. So all of these models that we're talking about in this talk are about taking a chemical structure and producing chemical hazard labels. So these labels are the UNGHS labels, Global Harmonized System labels. This gives us a common language to talk about, and we're really just talking about the labeling that people give these chemicals. So a lot of the data we pull comes from regulatory sources, and those are sources where people have used a variety of different tests to determine a label for a chemical. So that's what we're talking about here. I was fortunate that some people talked about machine learning before me, so you've kind of seen a lot of this, and I suspect many of you are familiar with it. Just briefly, when we're taking a chemical, and I'm going to keep everything at a pretty high level, come ask me if you're interested in details afterwards. When we take a chemical and we want to build a machine learning algorithm for it, well, we need to get it into linear algebra space, right? We need to be able to create a mathematical vector for it. So the way we do that with chemical structures is we take that structure and we find different substructures within that structure that we think might be predictive of various outputs. So functional groups are what those are called in toxicology. Here you can see an isobutyl group and a methacrylate group in two different colors. We use PubChem2D and Max for that. We're actually backing out of this, which is something that I'll talk about at the end of this talk if I still have time. Okay, so we use these structural features and we actually use them to develop similarity between chemicals. We use something called the Jacquard distance for that. And let me stop and back up just a second and tell you who we is. So these models are being built with Underwriters Laboratories, and they actually came out of my PhD thesis work with Dr. Thomas Hartong at Johns Hopkins. So that's who we are, and these models are developing quickly. You can access them at ulcomtoolkit.com. If you're interested, just come talk to me. You need a beta account for that. So that's who we are, and there we go. Yeah, so we have these chemical structures, and we want to say we can build chemical similarity between them. There's just a simple mathematical function that lets us do that. Once we have similarity, we can start doing some real magic with your chemicals. So our database is pretty large right now. We've got about 200,000 labeled chemicals. And when you give us a chemical to predict for, we take your chemical and we compare it to all 200,000 labeled examples. And we say, does your chemical lie in a space where there are a lot of chemical hazards? Is it close to a mutagen? Is it close to a non-mutagen? Is it close to an acute dermal hazard? There are about 74 of these hazards that we cover. And from doing this process, we build a feature vector that's about 148 dimension feature vector. So this is a vector describing the similarity space of your chemical of interest. All right, so that's how we create vectors. This is maybe a little dry, but it's really important because this is essentially the basis for all the models that we build, right? So we have a feature vector for a chemical. Now we can start plugging that into algorithms. All right, so this is my first paper as a PhD student in 2015. And in that paper, I was coming in with a computer science and math and physics background, and really just starting with toxicology. And I did this with a few people in Dr. Hartong's lab, and I was a little disappointed. You know, the amount of data that was available to build these models for skin sensitization in this case was about 100 compounds. Now, there are a lot of problems with that. One problem is that it's pretty hard to build a good algorithm with that level of data. But the bigger problem that others have referenced is that you can't really generalize something like this. If you're going to do cross-validation or some sort of internal validation on your model using a small data set like this, there are about 100 million compounds that are listed in databases. You're not going to generalize a 100 compound set to that. You might be able to learn some lessons. You know, you pick up that within this special case, and let me be clear, 100 compounds is always a special case, no matter what, right? But you might be able to find some functional groups and then make some arguments about why those functional groups matter for predicting things about chemicals, but it's quite limiting. So in 2016, we were looking for more data, and the source that we went to was REACH. REACH is legislation in Europe that requires chemical companies that produce chemicals in excess of 1 ton per year to register those chemicals and tell you all about their classification and labels. It's a super ideal data set for building models of classification and labeling. So our data set for skin sensitization went from a couple hundred compounds to 3,000 or so. You can see how you can start generalizing a lot better. So let me describe what these figures are to you. Every circle here is a chemical, and chemicals are attached to each other when they're quite similar to each other. And then they end up getting laid out according to how similar they are. So, you know, all the chemicals in this little cluster are all kind of similar to each other. Same with these chemicals. These end up being methacrylates mainly. And then you can say a lot about these chemical structures. Now there's a network effect here. Same sort of thing you've heard with the telephone or with Facebook. As you start adding data to these systems, the probability that the next chemical you add will be similar to a chemical in your current database goes up. And so as you collect more data, these models sort of exponentially get more valuable. And you can see that sort of visualized here. But actually, even with like 5,000 compounds, that's still a special case, right? We're talking about 100 million compounds that we're trying to generalize to. Something special to point out when we're building models off of structural data is that while there are a huge number of possible structures, it's a countable number. And I mean that in the sort of mathematical sense. So, 100 million, there's only so many ways you can build a compound out of a few different atoms, right? So you're not talking about like a smooth spectrum. All right. So the basic name of the game that you'll see in many publications is like, let me take this data set I have for skin sensitization, plug it through some sort of algorithm, and that gives me something like a neural net. We do that, and that's actually available right now if you go to that tool that I referenced. So this data set for our skin sensitization model, we'll be able to say, build a neural network that predicts for methacrylates and says, okay, methacrylate is a skin sensitizer. That's useful. We still have to address the problem of how to generalize this kind of thing. One way to start addressing that problem is just go out and collect more data. So we actually do this for a lot of endpoints now. We do it for eye irritation, for instance. And this is the data set for eye irritation. These are actually subsets of our data sets, just to be clear. But the thing to point out is that we're talking about, for our eye irritation data set, we have about 15,000 compounds. For our skin sensitization data set, we have about 5,000 compounds. And the overlap between the two of those is like 2,000 compounds, right? So there's an interesting opportunity here, right? Like when we build this eye irritant model, we're only using the data for eye irritation. When we build this sensitizer model, we're only using the data for sensitization. And that's sort of the common thread that a lot of people use to build these models. Now, the thing is that if you build a really good eye irritation model, there might be things that that model learned to make its prediction that are useful for predicting sensitization, and vice versa. So you really want to try to leverage that learned information between the models. So I don't have time to go into exactly how we do that, but you should read up about transfer learning if you haven't already seen it. The idea is that we can take these models and we can actually use them to sort of inform each other. Same way people do, right? Like if I were trying to learn about what makes a chemical corrosive, I might talk to somebody about what pH is, and they can tell me how pH works, and then I can extrapolate that into my models of other things. So these models can kind of teach each other. And that's largely what our models do right now. And this isn't just like a 2 endpoint thing. We have a model for all of our 74 endpoints, and they're all teaching each other. So you get basically an as good or better effect, where models that are doing transfer learning are going to do as well as those baseline models, or they're going to do better. Now, this might strike you as an academic curiosity, but let me try to convince you that it's not. If you're trying to build a model for skin sensitization, you might expect that the data you have is going to grow maybe 1,000 compounds per year, or maybe it's going to grow 10% every year. So you're going to have more data to test your models on, to build better models on, and you might get excited about that. But if you assume, and this is a conservative estimate, that there are sort of like 1,000 other tests that are similar to those skin tests that you're collecting data with, well then the answer here is clear, right? Like if you're using this approach where you just build this one model, you're only going to have 1,000 new data points every year. If you're using this approach, you're going to have 1 million new data points every year. And this is not, this is not made up. If you go to PubChem and look at their compounds, you'll see there are 100 million compounds and 267 million bioactivities. That's a ton of test data on different compounds. This is probably going to keep growing very quickly. So if you're using this approach up here where you're only looking at the skin sensitization data, you're leaving the vast bulk of the data on the table. You really need to leverage that. Transfer learning is how we do that. So let's look at some numbers. You'll see this little tag down here. We version the data that we test our models on. And we have a name for this one. You'll see it show up a few times. This is our most recent one. And these are our transfer learned models. And you can see that they cover about 9 different endpoints. And this is just a metric for accuracy. So we're getting accuracies around 75%. The lowest one is skin corrosion. I'd be happy to talk to you about why that one's kind of low. Our best one is acute aquatic. It's 91%. So these models really work. If you're measuring their accuracy on this holdout set test that we never built our models on, they're really generating output. But the problem with this approach is like we're building this model on data we collected, and then we're holding out some data and we're saying, okay, we're going to test it on this data that we never built our models on. But they still kind of come from the same source. So we're collecting all this data from regulatory sources. So the next step was like, how do we start getting more comfortable with these models? How can we convince other people that these models are useful? So one thing we did is we went and we took data from other regulatory sources and we said, okay, does the model still work on that? So we took data from this Japanese regulatory agency that has mutagenicity data, And we got about a 75% accuracy, a similar endpoint to genotoxicity. The accuracies were really similar. So that's good. But then we got 3 companies to give us validation sets, and our accuracies were quite poor. 66% up to 67%. Still a little bit of signal there. These are good models, but they're dropping a lot. And this is sort of to be expected, but that's a pretty big drop, right? And this is a real world test. These companies are the companies we want to actually use these models for whatever internal uses they might have. So why is that happening? Well, when we look at the validation sets they sent us, we saw a lot of drugs. We saw a lot of things that don't really fit into the regulatory data that we train our models on. And in this field, this problem is called a domain applicability problem, at least in chemistry. It varies by the field that you're looking at. So the question is, how can we, before we run a validation set through, look at these chemical endpoints and say, hey, that one the model will work pretty well for, and this one the model won't work all that well for. So we developed a pretty quick way to do that. Let me check. When actually are we going on time? Can someone tell me that? I should have asked. Okay, we're going to speed up a little bit. All right. I'll probably skip some slides at the end. All right, so we're trying to determine whether or not your prediction is, your chemical and endpoint is something that we're willing to predict. So when you give us that chemical, the first step we do is we compare it to the existing chemicals in our database. And that's how our models make a prediction, based on that comparison in a neural network. But now, to determine whether or not we trust our model, we actually take all of the unlabeled data that exists on PubChem right now. That's our source for this. So we query 100 million compounds, and we say, give me all of the compounds that are similar to this target, whether or not they have label data on them. So this are sort of the known possible structures for chemistry. And again, I'll point out that there's no white noise here. There's a lot of really interesting structure that comes into this process. All right, so what we're going to measure is how self-consistent the model is. Is the model saying that chemicals in this region are always going to be green? Or is it saying, maybe if I look at the really similar chemicals, yeah, most of those are green. So this is a pretty consistent area. The model is saying the same thing over and over and over again. That increases our trust in the model. Or it could be a region where you have a lot of non-consistent results. We'd have a hard time trusting these models because these highly similar chemicals, they're only differing by maybe one atom, maybe a bond has changed a little bit. We wouldn't expect sort of the high-level properties we're seeing to change across that unless we're in sort of a difficult space for these models to work. All right, so that's a heuristic for this. And yeah, we have basically a little algorithm that we run that generates this, right? But we have to measure and see if it's actually doing what we want in a domain of applicability algorithm. So our DOA, domain of applicability, should define where the model is correct. Where can we trust the model? So let's just define that mathematically really quick. So we're going to say that a DOA metric on a prediction, so prediction A, if it's greater than the DOA on prediction B, then we should expect that the prediction that the outcome for prediction A is more likely to be correct than the outcome for prediction B. So let's go ahead and look at that on our holdout set. This is data that our models were not built on. We've got this self-consistency measure. We call it the EM agreement. If I have time, I'll tell you why. So if we take a look at the 50% line, the blue columns here are counts of the true predictions in our holdout set. The red columns are the counts of the false predictions we got wrong. So all the way over at 100%, the chemicals that are very, very consistent in their prediction, these predictions are almost always correct. And actually, most of the incorrect predictions end up near the 0% line. So this consistency heuristic is really good for improving our accuracy metrics. Let's go back to our holdout set and see what happens when we refuse to predict anything that falls below that 50% line. Our accuracies really go through the roof here. So we've got 97% balanced accuracy on acute aquatic. Every accuracy is over 90% now. So for those accuracies to increase that much, you have to give up something, right? So we're refusing to make some predictions now. That reduces our coverage. Our coverage does drop significantly, so we're down to about 80% coverage. If you're looking at a chemical that sort of fits into the holdout set, that is a reasonable chemical to put it into this data set that we're testing on, then we're only going to cover it about 80% of the time. Still pretty good, especially for that kind of increase in accuracy. Let's go back to our companies. Actually, the data sets our companies gave us come up to 97.5, 100, and 100. Now I want to emphasize that there's no fitting process there for this heuristic. This isn't some sort of algorithm that we've overfit to that company data. You don't have to trust me that we're not training on that data because I've just described a heuristic that is not a training process, right? So these accuracies are coming from just refusing to predict for many of the chemicals that those companies gave us. So I told you before that when we looked at those sets, that a lot of those chemicals looked like chemicals we wouldn't be able to predict for. Well, you can see that here because the average coverage is only like 67 to 70%, whereas over here we've got about an 80% average coverage. Okay, so I think I'm going to cut off. Well, no, I got a timer here. I didn't realize that. All right, so we've got. I want to give you an example of why this works. I've described a heuristic, and I want to figure out how we can build a machine learning algorithm into that. I hate heuristics. I'm always trying to get rid of heuristics. I want to make it so the machine is learning those heuristics as well as possible, right? Because a heuristic is something that some sort of expert came up with, and if I'm using that expert, that heuristic, I have to trust the expert. That's a problem. So why does this work? So if I look at a chemical, trifluorobenzonitrile here, and I look at the labeled analogs we have in our database, I can't really tell a whole lot about what's going on here. I see that there are labeled analogs that are red and green, and this is real data, by the way, although it's sort of displayed in a hard to understand way. But this is the target chemical, and you can see the labeled analogs. So I'm going to do this process of throwing all the unlabeled analogs onto the set. So these are chemicals that we don't know anything about, but we do know their structure. All right, so let's hope that animation works. Great. So what you'll see, if this works, is that the space it kind of becomes much better defined. Right now we can see that there's a whole region of chemicals that are near our target that we don't have any data for. Right? That's really important to know for a machine learning algorithm. Let me skip that so it stops. Okay, we can also see that there's sort of three clusters of chemicals here. This cluster right here, it's got a whole lot of reds in it, and it's got a lot of dangerous chemicals in it. This cluster over here, it's got a lot of greens in it. Maybe this cluster is a little bit safer than this cluster is. And it looks like our target is closer to this cluster, although you'd want to do that in a quantitative way rather than looking at a graph. Okay, so this would be an area that we would say has a low self-consistency, but actually if we look at it as a human, we might say, yeah, I understand why this is low self-consistency. If I draw that circle of 80% around this thing, I've got greens and reds, but maybe I should trust this area a little bit more. All right, so if we go ahead and cluster those chemicals and just pick a few representations there, we can see this orange group has fluorines in it, and it's got these triple bonded nitrogens. And if we look at our target, if we compare our target to this cluster, and that cluster, I would argue that maybe this cluster is the best, right? So these are sort of subjective arguments. What I'm trying to point out to you is that by including data just about structure, about nothing else, we can really start improving these algorithms because they can learn what makes a chemical, what's possible in that space. So there's an algorithm that does that, and that's called expectation maximization, and there are other approaches for that as well. So that's one of our big next steps. 1 minute 30, okay? So our other big next step, at the beginning of this talk, I talked about how we have these feature descriptions, these sort of substructure descriptions of chemicals that we build feature vectors out of. I want to show you the first 10 dimensions of PubChem2D. PubChem2D is that thing that builds a Boolean vector out of a chemical, right? So those first features are saying, does the chemical have more than 4 hydrogens? Does it have more than 8 or 16 or 32? Those are really redundant, right? And there's no reason that we know that these are useful features for predicting something. And so really we want to back out this expert judgment about having more than 32 hydrogens matters for some reason. So how do we do that? There's a process called graph convolutional networks that we're integrating right now. Basically, we take your chemical structure and we represent it with an atom matrix and an adjacency matrix, where that atom matrix is telling you what atoms are in that structure. The adjacency matrix is telling you the bond structure of that structure, which atoms are bonded. And then we say that atoms are bonded to themselves just for math reasons. Once we have these matrices, we can plug that directly into our neural network infrastructure. So this works really well with what we have already built. Neural networks are really nice in this space. Okay, so let me keep going. I really suggest you read this post if you're curious about this by Thomas Kipf about graph convolutional networks. They're probably going to be a really big step forward. Just to show you one test we've done using some open source graph convolutional network software, this group at deepchem.io does really amazing work. We sort of took what they have out of the box, ran it on our training data, tested it, there it is again, 1.5.0, to compare it to our internal models. And out of the box, these GCN models were doing almost as well as our existing models, even better on skin sensitization and genotoxicity. All right, I'm going to skip this one. This is my last one. All right, so just to summarize quickly, this is actually available on ULChem Toolkit, Toxtrack.com. If you want to get access, though, you got to talk to me or talk to UL. Or we can work together on things, too. Could do that. All right, we talked about transfer learning. I try to make an argument to you that if you're doing an algorithm that isn't using transfer learning, at least in the space of chemistry, if you're not already falling behind, then in 5 years, you're going to be using less than 1% of 1% of the available data to make your models. Okay, I talked about this unsupervised DOA, this ability for this proposed heuristic for saying this is a prediction we trust, this is a prediction we don't trust, and I give you a quantitative demonstration of it. Things that we're finishing in 2019, I talked about how we can work in expectation maximization into these models. I talked about how we can remove that reliance on expert-defined features. And I didn't talk about how we're loading up tons of validation sets into this thing. And if you've got one, you should really let me know because we can see if these things work. Okay, that's it. This is a big team. These are the people I meet with every week, but there are a lot more people involved. Underwriters Laboratories is supporting this work. Thomas Hartong is my previous PhD advisor, and he also helps a lot with this work still. And Dan Marsh, it's a great picture there. He's one of the co-developers on this project. Okay, thank you.
We have perhaps time for one quick clarifying question if there are any. Otherwise, we can move on.
Just for the online
Wade Home from FDA's National Center for Toxicological Research. I'm just curious, when you transfer learning, I totally agree with you. This is something we really need to focus on in the toxicity landscape. But my question is, if you drop some of the endpoint or put back more endpoint, what does the reproducibility looks like?
I need you to define that a little bit more. You mean the reproducibility for predicting like one endpoint?
Yeah, so see the results, how
okay,
reproducible.
so like if we add a model and then we subtract that model off?
Yeah.
Basically what we're seeing is that there's like a lot of sensitivity to how we add these models together. One example I'll give you is that skin corrosion data set we have, that's our biggest data set. We have a ton of data on skin corrosion from the regulatory sources, right? So that model for skin corrosion ends up increasing the accuracies for our other models by a significant portion. Now, occasionally, some of our smaller data sets actually decrease the accuracies for our models. That's called negative transfer, and that's a possibility. So this is a really active place of research right now. You can think about like, if you're a human and you're trying to combine ideas, combine mental models, I understand pH, how does that apply to corrosion? You're really good at figuring out these are related concepts that should be useful for each other. It's harder to do that with this infrastructure. But the thing I'll say about neural networks, and I know that they're like peak of the hype train, is that they're really, really flexible, right? So you can integrate like a genetic algorithm for trying to figure out which modules you should be pulling into another module for transfer learning. You can integrate all these feature selection tools on the sort of the level of the model. So, right now, there's sort of a basic approach we've defined for doing transfer learning that gets us as good or better models after doing it. But I think in a few years, you'll see many better approaches. Thanks.